Hi, John here. I just want to do a short video today about hydroelectric turbines. I'm going to show you guys and girls the three main types of turbine, and also I'm going to tell you about the design considerations so you know why we're using each type of turbine and where you're likely to see each type of turbine. So let's first just briefly go over what a hydroelectric turbine is. Now, hydroelectric turbines convert potential energy to mechanical energy. They do this because the water passes through the turbine across a runner or onto a runner, and this causes the runner to rotate. The mechanical energy then from the runner drives a generator, and then we turn the mechanical energy into electrical energy. Obviously you can also use the shaft to drive other things such as a pump, but hydroelectric turbines, as the name suggests, generate electricity. They're hydroelectric. The amount of energy that can be converted depends upon several factors, such as the available head. This is the amount of water above the pump, or the height of the water above the pump, the flow rate through the turbine, and the efficiency of the hydroelectric turbine itself. Now, hydroelectric turbines can operate at a wide range of pressures and flow rates, but there is no single turbine that can work at all pressures and flow rates. So you have very different and distinctive designs depending upon the conditions in which the turbine will be operating. The three main types of turbine that you're likely to see are the Pelton turbine, the Francis turbine, and the Kaplan turbine. The Francis turbine is the most common. It was designed in the mid-1800s by James B. Francis. The Pelton turbine was again designed in the mid-1800s, this time by Lester Pelton. It has by far the most distinctive appearance or shape of all the turbines. And the final turbine is a Kaplan turbine, which was designed by Victor Kaplan at the start of the 1900s. The Kaplan turbine looks more or less like a propeller. Less common types of turbines would include the Darius turbine. Darius turbine was designed in the 1900s by Paul Darius, or Darius, depending on how you pronounce it. But this is not considered one of the main three types of turbines. This is not in the main group of turbines. You're much more likely to see the Francis, Pelton, or Kaplan turbine than you are the Darius turbine. Another sub-turbine would be the cross-flow turbine, but again this does not belong to the main three. Hydroelectric turbines are classified into two main categories as either reaction or impulse type turbines. The reaction type turbines are pressure turbines. They have a continuous body of water, an unbroken body of water, from the suction side or from the upper reservoir all the way down to the lower reservoir. The water body is unbroken. These are pressure type turbines, and the reaction turbine functions because as the water flows through the runner, there's a pressure difference between the suction and discharge side, and this pressure difference causes the runner to rotate. So that's the reaction turbine. Just remember, reaction, pressure type turbine. Impulse turbines are pressureless type turbines. They work by shooting a jet of water at the runner. What they actually do is they direct the jet tangentially into a bucket, and this causes the runner to rotate. So remember, impulse turbines, no pressure, and also the body of water is broken. We're taking it from the suction side, we're then shooting it at the runner, and this causes the runner to rotate. The water is then just drained away. The reaction turbines, the whole process is a lot less dramatic. The water just flows through and the pressure difference causes the runner to rotate. Two different categories, and the only two categories that you're going to see. I should mention at this point that the runner is the part of the hydroelectric turbine that converts the kinetic energy to mechanical energy. So the runner is going to have different shapes. It could be a Pelton runner, a Francis runner, a Darius runner, or a Kaplan type runner. Just thought I'd better explain that there because there's a lot of terminology that people throw around, and for me personally I find it confusing, and I actually have a rough idea what I'm talking about. I can understand if people get slightly confused. Anyway, let's carry on. Hydroelectric turbines are also classified by not just their design or operating conditions, but also by the head. Low head would be, for example, up to 30 meters, so 0 to 30 meters. Medium head would be 30 to approximately 300 meters, and a high head would be anything above approximately 300 meters. You can also classify turbines by their orientation, if they're vertical or horizontal, and by the shape of the water passage through the turbine. So, We've discussed a little bit about each type of hydro turbine, or the main types of hydro turbine, and we also know that they fall into two broad categories, such as impulse and reaction. Now we're going to look at why you have the different designs and when you'll use them. So the graph in front of us, it says hydro turbine design in the title. On the left hand side we've got head of pressure going from 0 up to 2000, and on the lowest scale here on the x-axis we've got the flow, which is in meters cubed per second. So we'll start at the bottom. We can see here we've got a horizontally orientated Kaplan runner. Now this would be installed, for example, for a bulb turbine, so I'll just refer to it as a bulb turbine. We can see that it's on the lower end of the scale for head of pressure. It's going from about 5 up to 25. See, the scale starts on 5 because you actually need some head of pressure in order to get some flow. I mentioned earlier in the video are from 0 to, for example, 1000 meters, but obviously at 0 there's no flow. You really need to start at, say, 5 just to get some movement or a decent amount of water flowing through the turbine. So this bulb turbine would operate on a range of, say, from 5 meters of head up into about 30 meters of head. And we can see that on the lower scale it needs a flow of a minimum of 1 meters cubed per second up to a maximum of about 200 meters cubed per second. So when are we going to use this type of runner? We basically need a very high flow rate, but we don't have a large head of pressure. So it would make sense to use this for a run-of-the-river power station. If we've got a river, we could easily dam it slightly, create this 10 meters height drop. This means we have 10 meters of head, and this would be enough for our bulb turbine. The river, if it has a very high flow rate, and a lot of rivers do, then that's ideal for our bulb turbine. That's exactly what we want. We want a high flow rate, but we also want a relatively low head of pressure. And we're going to get that when we install the bulb turbine in the middle of a river, for example. Another good application for a bulb turbine is for tidal power generation. The tide's only going to rise by, let's say, for example, between 5 and 10 or 5 and 15 meters per day, and then it's going to flow back out again. So you'll have a high tide and a low tide, but there is a lot of water in the ocean. That means you're going to have a very, very high flow rate. The water's rushing in twice a day and rushing out twice a day, and if you've got a head of, say, 10 meters, that's more than enough for this bulb turbine to function. And that's the exact conditions that the bulb turbine wants. If we go a little bit higher up the food chain here, or a little bit higher up the graph, should I say, we've got a vertically orientated Kaplan turbine. Now notice that this guy can operate to a much higher head of pressure. He's up here in around about the 80 meters head of pressure range, or maximum, and the flow rate, he can do very, very high flow rates, up to 1000 meters cubed per second. So the vertically orientated Kaplan turbine covers this entire section here, and what's not shown very well in the graph, but it also comes down to the base here, so between 1 and 2 meters cubed per second. So you're going to have a very large number of applications where you can use the vertically orientated Kaplan turbine. So it crosses into the green area, the red area, and it has a lot of its own area here on the right hand side. Remember, the medium head of pressure range is from about 30 to 300. So this guy's sitting comfortably in the middle, although he's also covering the lower head of pressure ranges all the way down to 5. So that's the vertically orientated Kaplan turbine. We'll go slightly higher now. We can now see a new type of hydro turbine runner. It's this one here. This one is a Francis runner. Of all the turbines, the Francis turbine has the widest range of applications. We can see that clearly on the graph here. The red area goes all the way down to a head of pressure of about 18, all the way up to a head of pressure of about 750. And you can see on the flow rate that it can cover almost the entire graph from left to right. Flow rate here of less than 1 meters cubed per second, all the way up to 1000 meters cubed per second and beyond. So this is a very versatile turbine. The Francis turbine is the one that you are most likely to see. It's the most common turbine in the world, and that's simply because it can operate across such a wide range of pressures and flow rates. The Francis turbine is also what I dub the secret turbine. The secret turbine has two functions, or it can have two functions. If you have a radial flow Francis turbine, you can also use it to pump water. So it's got two functions, or it can have two functions by design. That means if you're taking water out of an upper reservoir to a lower reservoir and it's passing through the Francis turbine, you can generate electricity. But where the secret turbine comes in is that maybe you have too much electricity in the grid and you want to use some of that electricity to pump the water back up. And to do this, you'll normally use a radial flow or a Francis type runner or a Francis type turbine. It'll pump the water up. Let's say, for example, it costs 1 cent per kilowatt hour to pump the water up, and then they'll let the water back down when it costs 5 cents per kilowatt hour. So they're making money. They're pumping the water up when the electricity's cheap. Remember, they need electricity to drive the runner and pump the water up the hill back up to the upper reservoir. But then they've done all that when the electricity was cheap. They'll let the water back down when the electricity is expensive and they can sell it back to the grid. And that type of operation is referred to as pump storage. And we'll move up now to our final hydroelectric runner type, and that is the Pelton turbine. Zoom in and get a good view of it. Pelton turbine, very distinctive shape. And this is used for high heads of pressure applications. It's right up here in the top left. Generally, you're going to see Pelton turbines when you have a very high head of pressure and a low flow rate. The Pelton turbine, because it can operate efficiently at such a high head of pressure and low or relatively low flow rates, it's an ideal candidate for when you have a very high upper reservoir and a very low lower reservoir. This means there's a very large head of pressure or a difference in height between the lower reservoir and the upper reservoir. If all design considerations have been done correctly and you've got a Francis type or a propeller type turbine operating at maximum efficiency, you should get an efficiency rating of about 0.93. For Pelton and tubular type turbines, you're going to end up with a maximum efficiency of about 0.9. Anyway, I hope that tells you a little bit about the three main types of hydroelectric turbine, and you should also understand now why the designs are so different and why they have such distinctive and different appearances. If you've got any questions or comments about the video, please do get in touch. Thanks very much for your time.